Yeah, thank you very much, Stephen. And hello, everyone, and welcome to our webinar in this afternoon or in the morning, wherever you are. So we will talk about the photomultiplier simulation, and basically the whole webinar is meant as a proof of principle that we can simulate this. For those of you who might not be familiar too much with a photomultiplier itself, let's have a small or short introduction what it is for and what are the typical application examples. The purpose of a photomultiplier is the enabling the observation of low-light scenarios in real time by pure eye. For example, a very obvious application is night vision here in this case. Or a photomultiplier can also make non-visible spectra visible, as for example infrared or gamma rays. As you can see, the application examples, as mentioned already, is night vision, or it's used in several scientific measurements. For example, the scanning electron microscopes uses a detector where a photomultiplier is built in order to amplify the secondary electron current, which finally generates the picture of the scanning electron microscope. Another scientific measurement example is here the MAGIC telescope at night, which is basically used to observe gamma rays, which are emitted from black holes or from stars, and to understand the behavior of the space. So in each of these, the rays which are coming to the telescope here are then amplified by the photomultiplier. So how does it work in principle? We have a basic principle sketch here. And let's have a look at the different, let's say, stages in detail. So the thing is, in yellow here, we get some low-level light which illuminates a material. As you might know, the light is can be characterized by its photon energy, which is the Planck's quantum times frequency. According to the photoelectric effect, which was first described or explained by Einstein, this light can hit out electrons from the material. The kinetic energy of the electrons which are hitted out is the energy of the photon minus the work function. The work function actually is a measure how difficult or easy it is to release an electron from its crystal structure. As you can see, if the photon energy is too low, then it cannot exceed the work function and no electrons are released. The material where that happens is actually called the photocathode and can be either transparent, meaning the light shines on and the electrons go to this side, or reflective, as you will see later on. The so generated photoelectrons, as you can see here, will be guided towards electron multiplication stages. Eventually, the electrons can also gain some energy on their path by additional applied electric fields, which is not in the sketch here. These electron multiplication stages will then amplify basically the number of electrons, and you get more and more electrons out. These electrons will then be guided again to a phosphor screen or any other screen which converts the electrons into light. So effectively, the photomultiplier is not only something which amplifies light, but internally it also amplifies electrons. Let's have a look at the necessary details inside the software. That's actually something coming up in the new version, which is currently going out. And there the photoelectric effect, which obviously is necessary for this workflow, is implemented. So how does that in detail work? So in the software itself, we would define an emission model. So typically the emission models are for particle emission, but as the photon, the light, will be converted into particles, this light source is actually an emission model. So you can see here we have in our emission model something which is called optically induced, There you can specify the wavelength of your light and the total power. As you can see from the dialog, currently we have only one wavelength available. Of course, in the future we might have, let's say, multi-frequency light here. But currently there's a monofrequent light. And then you see the rays, which is basically our source of the our light source. This alone doesn't give you photoelectrons, because you need to, in addition, define also your material. You need to define your photomaterial. In order to do so, we have in our material property dialog, we have a special tabs for particles, and there you can specify optically induced emission, which is a material property. You can specify here the work function. Remember, if your light has energy lower than the work function, no particles will be released. The material, the photoelectric characteristics of the materials can be either determined as radiant sensitivity, as shown in this graph here. Radiant sensitivity basically means how much photocurrent you get out of a certain number of power of a certain wavelength. Or you can specify quantum efficiency, which is a percentage on how many photoelectrons per, let's say, incoming photon are released. You can either import your specific material properties as shown here, or you can also specify a constant value. As discussed before, typically you will have some certain point of cutoff where the higher the wavelength gets, basically you will not get any particles out because it's lower than the work function. So in principle, you can estimate the work function from this plot here. Okay, so you have to find your light, and then you have to find your materials. And then you can basically run the solver, currently the tracking solver for that. And the solver does actually two things in one. The first thing, it does a simple ray tracing algorithm as shown here on the left. This ray tracing basically finds out which areas or objects are illuminated by the light. So you can see here this face is illuminated by the light, and this one, and then some light rays just penetrate through because there's no object in between.
Okay, so
once
we
the
have...
solver,
Sorry.
Yeah.
We have...
once the...
Oh, sorry, continue.
I'm not... Yeah, okay. Once we have, we know which objects or which areas are illuminated, the solver basically automatically calculates the photoelectric particles which are emitted. This is the second step here. So you see, if we have a 3D object, as shown here on the upper part, we will get reflective emission. If we have a 2D object, a sheet object, we will get transmissive electron emission. This was built in order to mimic actually the transmissive and reflective behavior of photocathodes. So you can do two things here. Okay, I guess now it's time for the poll.
Sorry about that.
No problem.
So this question for all attendees. What's your motivation for watching this webinar? Are you watching out of a general interest in the topic, or are you currently working on photomultipliers? Okay, so we have the results of that question. And would you like to read them, Monica?
I can't, I don't see them.
So the majority have said that they're watching out of general interest. 13% are currently working on photomultipliers.
Cool. Very nice. So yeah, that was approximately what I was expecting. So therefore we tried to find a mixture also between detailed studies and general overview here. Okay, then let's continue here. Okay, so this is what you need inside the software. Let's go back to our structure and have a look at what the principle, how the basic structure looks versus our simulated structure. So on the lower right here, we see what's going to be simulated in the next slides. And in order to identify which parts are what, I have basically written here the color code in here. So we have the light source, as shown before, which illuminates the surface. We have here the transparent photocathode, where the light particles are emitted. Then we have here the electron multiplication stages, which I will explain in a second in more detail. So this is actually the crucial part also of the structure. And then at some point we get more electrons out. What's not included in the software is this conversion of particles again back into light. Okay, let's have a little more detail in how the amplification works. So as said, we get some photons in here. They hit the photocathode, in this case transparent photocathode, and then we get a photoelectron out. So in principle, all the blue rays are electrons, but there are different causes for the electrons. So this is a photoelectron from photoelectric effect. This photoelectric effect hits a first so-called dynode. This object basically is made out of a material which can release secondary electrons when being hit by a primary electron. That's actually, I guess, for almost all or for many materials the case, that you have can have secondary electrons released, and the material characteristic is a so-called secondary emission yield, which is actually an amplification factor. So what's the secondary current depending on the primary current? So your photoelectron is coming in, hits out, for example, two secondary electrons. They, by their electric field, are guided towards the second dynode and hit out again more electrons. And then this continues so on and so forth along the dynodes until you get many electrons, many secondary electrons. Okay, so let's have a look at the dynodes in more detail. So the dynodes in our case here are the turquoise things with the secondary electron emission material, and they actually amplify the current. And we have kind of multiple stages in order to have more and more current. These magenta objects are grids, which basically are meant to give a good field distribution and to prevent some particles by the field distribution to go back. These grid objects are actually transparent for the particles, so they will not hinder particles from going through. Then we have here field shaper, which makes the field quite nicely, so in order to guide particles really on the surface here. And then we have a photocathode. This type of photomultiplier is also called box and grid type, in case you want to look at it later on. So the material of these dynodes, as said, is meant to amplify the electron current. So we see here the SEY, which typically is described in terms of how much current, or what's the amplification factor of the current versus the input or the collision energy of the incoming particles. With that, maybe in a more linear view, we can also estimate the ideal current amplification for the structure. So if we assume in an ideal world all particles would hit, let's say, the dynode at the maximum, with an energy where we have the maximum SEY, and we do this as many times as we have dynodes, we would get the ideal current amplification, which of course in reality we don't get, because not all particles have same energy, and maybe we also lose some particles. For the first studies, actually the photoelectric effect is not taken into account, but as emission source is just a fixed emission here assumed from the surface with a low with a no energy value and a certain kinetic spread here. As input current, I've used 10 microamps, which is already quite high if you remember that the photomultiplier is used in principle for low light scenarios, so for low current situations. Okay, the first steps you certainly want to analyze is how does your field look like, because the particles only follow the field. So the first thing you certainly would do is to analyze the electron optics. So you see here on the left, actually both pictures look quite similar, which is also good. But on the left is the sources you apply. So you have your structures, and then you specify on each of the objects what the corresponding potential on this object is. And with these sources you get a resulting 3D potential, which in this case here is just plotted in a 2D plane. You could of course also look at the electric field values, but that for this webinar didn't give me too much more additional information here. And then with these field or potential values, we can actually let the particles go through the field, and this looks as follows. So remember, we had here the DC emission of our photocurrent, and then you see here the trajectory of the particles in this electric field. Maybe for those of you who are not familiar with our trajectory plot, you see here kind of the path of the electrons emitted, and the color indicates, in this case, the energy of the particles. So you can see they start quite slowly according to their emission energy, and they get accelerated towards the first dynode, where they then hit around 300 electron volts. Remember, that was exactly the collision energy where we get a high secondary emission yield. And obviously interesting factor for photomultipliers is how many electrons you can guide to the first dynode here in the middle, because the idea is not to lose too many particles already somewhere here, because your field is maybe not shaped well. So you can see here in this plot that we have a so-called collection efficiency of 100%. So all particles here are finally going to the first dynode, where then the amplification process starts. Maybe you can already remember, because we see something different later on, that we have here a normal emission towards the surface. What you can also see is that all particles land approximately in the middle of this dynode, which then gives a good emission angle for future, let's say, for future movement of the particles. So this is already maybe nice to see where your particles land initially, but of course you want to have see the amplification effect, and therefore you need to enable a secondary electron emission material. So you can just disable and enable it. The thing is, you see here already that some particles, very few particles come in, and then the trajectory plot gets more crowded and crowded. If we look at a cut view and also scaled a bit differently, we see this quite nicely, that here we have very few trajectories, here already more, and then more and more. If we look at the crashing energy, also there it's everywhere between 0 and 400 electron volts, as remember where the maximum SEY was. So we can see here quite nicely an increase in particle density, and therefore we can already identify an amplification process. Of course, maybe this is a bit vague information to look at the trajectories. You might want to have some numerical information. And of course, you get this as well. So the first thing which you can look at is, which actually is derived from the trajectory plot, is the particle current density plot. You see here the structure again in a cut view, where we have the anode here, then dynode 0, 1, 2, 3, and then down to 7. So 7 should have the lowest current, and dynode 0 the highest. You already see from the plot here, from the 2D plot, that the current density gets higher and higher, and we have the amplification. And this is already in a logarithmic scale here. We also get not only this information like that, but we also get the collision information on the different object, which is shown here on the right. So we can see that dynode 7 is this one here, where we have the lowest current, and then we get amplification more and more until we have this anode current of 1 amp. Remember, we're putting in 10 microamps. So with our templates, you can have our template-based post-processing. You can also get the number for the current amplification by reading in the anode current and dividing it by the emitted current. So we get around 1E5 current amplification. Remember, the ideal current amplification, which you can calculate from the maximum SEY, is around 2E5, which is not too bad, considering that not all particles land exactly in its optimal position and with optimal energy. Okay, so this is basically, these are the two ways you can observe the amplification, also in numerical values with a 3D current density plot or from collision information. So if we now include the light source, the picture shouldn't be too much different, although we see some difference. As said, we need a light source here where we have a wavelength of 500 nanometers according to our material. The material is defined here with a certain work functions, and actually for the sake of simplicity for this simulation, I've used a constant quantum efficiency. The value is actually inspired by values given in the Photomultiplier handbook from Hamamatsu, which is very nice and which you can download on the Hamamatsu website. Okay, if we do so, if we define the material parameters, and then we can also define the light source, which you see in more detail. We have 500 nanometers, as discussed before, and as total power, in this case, 1e-7 watt is assumed, which is approximately from the light density or power density is approximately full moon scenario. So it's already quite bright scenario here. So this given, basically, the solver calculates not only the trajectory, but it also calculates automatically here the emitted photocurrent, which might be interesting because so far you've given only the light. You want also to know how much current's coming out, and it also gives you automatically the currents at the several diodes. And if we compare that, okay, maybe going back, we see that we get as emitted photocurrent something about 2 microamps, and we get the same at the first diode. The sign is different because one you have current emitted and current colliding. But again, this is 100% collection efficiency. And this even though the particles are not necessarily emitted normal to the surface. You see here some particles are coming out with a certain randomness here. But the guiding of the field shaper in this case is so nice that all particles still land on the first diode here. Okay, then that was so far without the secondary electron material. Again, if we enable it, of course you can combine also the two features. You can combine the photoelectric material with the secondary electric material, and then you get a similar picture as before with the secondary electrons. And of course, also the current amplification in numerical values shouldn't change so much. You see here, first of all, the emitted photocurrent, and then we can also get the current at the anode, and the current amplification should stay the same because that's a characteristic of the structure here. What might be interesting to look at, of course, our anode current currently is smaller than the 1 amps we've got before because we have a smaller photocurrent than the assumed one initially. Of course, in both cases, we still see the amplification in 1D and 2D result, but here we can see a different current density according to the different emission and due to the photo emission, which is a bit more complex. And I think this is now time for the next poll.
Yes, that's right. So, is your design process mainly based on measurements, simulation, or on analytical predictions and expertise? we've got an interesting mixture of results there. 18% based on measurements, 42% use simulation mostly, and 39% are going on analytical predictions and past experience.
Okay, that was very interesting, and yeah, of course for us it would be nice if you all think of simulating, but let's continue what we can do as well here. So that's so far the photoelectric effect, the electron optics, and so on. So let's start analyzing what can we do in addition. So this photomultiplier might be used not, in free space or somewhere, but it might be used in the vicinity of electronic components which can generate magnetic fields. We should also consider our Earth magnetic field, which is in the order of 48 micro Tesla, and therefore, yeah, we might think of if the magnetic field has an influence. As you know, the electrons do not only react on electric fields, but they also react on magnetic fields. So in order to study the sensitivity of the device on magnetic fields, you see here the device, and basically a constant magnetic field is applied in all three coordinate directions where the value, the magnitude of this magnetic field is varied. And let's start with the direction here with this x direction. Then you see that if you have low magnetic field, more or less the current at the anode is constant. But even if we go in the order of the Earth magnetic field, basically the current drops already, and the current drops more and more the higher the magnetic field is, until we get here only until we've lost around 35% already. Let's have a look at the other direction. So the y direction, you see, has almost no influence. So this direction is very insensitive here. While again the z direction, so the two radial directions basically show similar behavior. So therefore, quite obvious idea is to shield this device, which is especially necessary for x and z direction. And the shielding could be done with some permalloy, which you wrap around the device, which is tried to be mimicked in this structure here. So this kind of brownish structure is an additional material outside of the photomultiplier with a permalloy-like permeability of 100,000. Outside, again, a constant magnetic field is applied, and then we can look with a magnetostatic simulation at the resulting magnetic field distribution. You can see outside we have 130 microtesla, and the permalloy with its high permeability quite nicely guides the magnetic field outside of the structure. Remember that the magnetic field is also applied in the z direction, which was one of the sensitive directions. If we look at the magnetic field not in this error plot, but in the contour plot, we can also hide the areas where the magnetic field is out of a certain scale, and therefore we can identify here that basically in this area the magnetic field is smaller than 1e-5 Tesla, which is actually already the range where it doesn't matter if you have an additional magnetic field. So the permalloy quite nicely shields the photomultiplier in order to make it work also under, let's say, all circumstances. Okay, this is maybe one interesting study, one interesting question in the context of this photomultiplier. Another one which I have omitted so far, which is also an important part, is the effect of the space charge. So you might know that if you have many particles, they form a space charge cloud, which can prevent new particles from coming out. And so far in our studies of the trajectory analysis and so on, the space charge was actually ignored, not included. If we enable it, which we can do in our solver, you see in principle not such a big difference here in the trajectory. So we see here our trajectory plot, and it increases in the density and so on. So there you cannot identify so clearly what's going different. But already if we look at the current density plot, you see that here we get an amplification, but from this dyno to the next one there's not so much more gain, let's say. And this becomes even clearer if we look at the collision information. So here from dyno 7, which is this one here, to the next ones, it's still quite nicely in amplifying, but now we can see that our anode suddenly starts to be here, and also the dyno 0 and 1. So you see the anode is actually not the object with the highest current, not even dynode 1, which is this one, but the current instead kind of gets stuck here at this dynode due to the space charge effect, because you have so much current in this case that you don't get any more gain. So we can see the saturation effect here. In order to, of course, you could say, maybe, I don't know, the simulation and the solver, but of course we can also verify that. And in order to do so, I've used a new solver, which is actually especially for space charge problems, which is a transient solver, and it's a so-called transient e-static pick solver. So far we've calculated with a stationary tracking solver, and here we go for the transient ES-pick solver. The first thing which you can notice is that now our trajectory shows a time dependence, because it steps through the particle movement and evaluates where the particles are going to end up. And then we can also estimate or analyze the anode current here, which is shown on the right-hand side. We get quite good agreement to the anode current of the tracking solver before, which is also around 0.013 to 0.015. So there's really a huge effect compared to the simulation where space charge was actually ignored, where we got 1 ampere out of the same simulation. What's maybe nice as well is that with this new solver we can also understand how long the particle takes to get here, and this we can see here, and which shows us the electron transit time through the photomultiplier. This is obviously of interest in order to understand the frequency behavior, or if you can use the photomultiplier in a high pulse situation. Because if it doesn't react fast enough, then maybe you should think about your pulse repetition rate. By the way, these two simulations are again done with a fixed emission of 10 microamps, just in case there's no misunderstanding here. Okay, of course, these 10 microamps which we have here is, as mentioned already earlier, already quite a lot. And the space charge effect gets more and more pronounced the more current we have. And of course, since this is an amplifier, the more current we get initially, the more space charge effect we get. And in order to understand that, okay, that comes later, you could do kind of a parameter sweep, which we'll do at the end. Let's say we have here in order to kind of work around the space charge effect, we could think of draining or getting rid of the particles more easily, because if the cloud is not so let's say if there are not so many particles anymore, the space charge effect is not so much more pronounced. In order to do so, you could increase the potential values towards the anode here. And this typically you could do with a so-called tapered voltage divider, and which is also inspired from the Photomultiplier handbook from Hamamatsu. So far, between all the dynodes, basically the same potential difference is applied. but towards the end of the structure, the potential difference is made higher in order to get away the particles and to have a particle drain. And to get away the particles. Remember here that this potential difference U is exactly the potential, or in order to have the particles colliding at the maximum SEY, where the maximum SEY is. So at the end, with a tapered voltage divider here, you have to find a compromise between particles crashing at the optimum energy, or between, let's say, removing the space charge cloud towards the end of the structure. If you do so, we still, of course, see the amplification effect. You see here already towards the anode, we have a better gain than before. And if we look at the numbers in detail, you see the anode still is not the maximum current, but at least it's 3 times larger than without tapering. And now our particles kind of get stuck not already at dynode 1, but already at only at dynode 0. So kind of here. So with this kind of modification, we have already managed to get more output current here and to remove, let's say, the particles more towards the anode. As said, the space charge effect basically is an effect which depends on the current, and of course the more current you get in, the more current you get here, and the more pronounced the space charge effect occurs. And in order to understand at which point this happens, we could do a sweep of the photocurrent and see how this affects basically the anode current. If we have a low photocurrent, then we get more or less constant behavior versus input current. So these peaks here is due to the stochastical behavior of the secondary emission. But the higher we have the input photocurrent, the more and more basically the anode current drops. Therefore, we see the saturation effect of the device. So this finally brings me to the end here, and the idea was basically to show you a proof of principle of simulations, what you could do for this application. You have seen the electron optics, which you finally get already with an electrostatic solver, the current amplification, which you could estimate with a tracking solver, the photo emission with tracking. You could analyze the impact of the space charge effect with the new solver, the ESPIC, or the tracking. You could look at the magnetic field. You could look at the magnetic field, and and you could look at the saturation characteristics by a sweep. All solvers are accessible on the platform and with the same GUI. And all simulations aspects here can be handled by CST Studio Suite. Okay, so thank you very much for your attention, and other questions.